The first problem I want to show you here and discuss with you is the following. It says two particles, okay, have the same charge. So these particles are charged, okay, and each one of them has a charge of 1 plus 1 microcoulomb, which means they are positively charged. Initially, they are held at rest. So initially, they are here, closed. And of course, this is Q1 equal plus 1 microcoulomb, and this is Q2 equal plus 1 microcoulomb. And they are held here fixed. This is the initial configuration, okay? This is the initial configuration, and they are separated by a distance of 1 centimeter. It says here, D equal 1 centimeter. This is the distance between the two particles, and initially they are held like this. Remember that these two charges are positive charges, so they repel from each other. Naturally, they are going to repel because there will be a force on this charge in this direction and a force on this charge in this direction, so they will repel, okay? They repel each other. If the charges, one was positive and the other one was negative, then they attract each other, okay? One of the particle is released. So initially, V1 initial is 0 and V2 initial is 0. Both of them are at rest because they are held at rest. One of the particles is released. Let's take this particle here. It's going to be released somehow, and it's going to move away, of course, and moves away from the other fixed particle. So this particle is going to remain fixed. When the moving particle is a distance of 3D, so if D is 1 centimeter, 3D will be 3 centimeters from the other particle. What is its kinetic energy? So that's the initial configuration. Let's look at the final configuration. So Q1 will remain here, but Q2 will be a distance here, which is 3D. So the distance now became between the two particles is 3D, which is 3 centimeters, okay? This is the final configuration. This is the final, okay? That's the final configuration. Of course, this particle here, Q2, is here, and V2 initial is 0 because this is fixed, and there will be a V2 final, okay? And he doesn't want the velocity or the speed, he wants the kinetic energy of this particle Q2, okay? So we know that electric force is conservative, okay? We talked about this when we were explaining the concepts, is conservative. What does it mean conservative? It means the change in mechanical energy or total energy of the system between the initial and the final states is 0, okay? And that's the change in kinetic energy plus the change in the electrical potential energy. So in this case, the change in kinetic energy will be minus the change in the electrical potential energy here, okay? So here is K final minus K initial of the two particles equal minus delta U, which is minus U final, the potential energy in this configuration, minus U initial, the potential energy in this configuration here. We're talking about electrical potential energy here. So it will be U1 minus UI minus UF. Now remember that initially the two particles are at rest, so this is 0. And finally, this is the kinetic energy of which particle? Since this is still keeping at rest, so it will be the kinetic energy of particle 2. So K2 final, which we are looking for, okay, is equal U initial minus U final, okay? What is U initial? The potential energy of the system, of this system here. Go back to the concepts when we were discussing the concepts. The potential energy of this system of particle is what? Is K Q1 Q2 over R1, the distance between them, minus K Q1 Q2 over R2, the distance between them, okay? So, of course, Q's, now we put the numbers, okay? So K, remember that K is 1 over 4 pi epsilon 0. This is a constant, okay? Coulomb constant. So 9, and it gives you, and this is 9 or 10 to the power 9. Okay, this is a Newton over. So the force is K Q1 Q2 over R squared. So to find the units of K, it will be Newton meter squared over Coulomb squared. You see, you bring this here and you bring this here, and you get the units for K. But anyway, let's put the numbers there, 10 to the power 9. Now, I multiply by what? By the charges. 1 10 to the power 6 minus 6 times 1 to the power minus 6. It gives you 1 10 to the power minus 12 over the distance between them initially, which is 0.01 meters. We have to use SI units. Minus 9 10 to the power 9 times 1 10 to the power minus 12 divided by, what is the distance now between them? Is 3 centimeters, 0.03, okay? So if you do the calculation correctly, you find that kinetic energy of the second particle here, the other particle, when the distance is 3 centimeters, is equal to 0.6 joules. This is plus 0.6 joules. That's the kinetic energy. Of course, the kinetic energy is always positive, okay? I don't even need to put the plus sign here, because we know the kinetic energy is always a positive number, okay? Because the kinetic energy actually is half mv squared, and mass is always positive, v squared is always positive, and therefore the kinetic energy is always a positive number. Thank you. Okay, this problem is the same idea, exactly the same idea, but this time he's looking for the speed of each particle. This is from, I remind you that these are all the exam problems. Two identical charged particles, this is the charge Q, 15 microcoulomb, it gives you the mass of the particle. You will know later why he gave you the mass. Are initially held at 1 centimeter away from each other. They are released from rest, as in the previous example. What is the speed of each particle when the distance between them is doubled, okay? Now we double the distance. So initially they are here, a distance d, and finally they are here, a distance 2d between them, okay? That's the point, okay? And of course they are moving here. Both of them are moving, not like in the previous, so they have v. Do you think they will have the same velocity? Yes, they have the same speed. They have the same speed, but they have opposite velocities. Velocity is a vector, so it has direction. But the speed here and the speed of this particle are the same. This is q and this is q. They are both of them are identical charges, okay? So both of them are positive, and therefore they are going to repel from each other. They repel, and he wants. So this is the initially. This is the initial situation, and this is the final configuration or situation. Okay, final configuration. Now, if I want to find the speed of each particles, we have to again use the idea of what? Of delta k plus delta u equal to 0. Okay, and because we have the electric force is conservative force, so the total energy of the system is conserved. What is the total energy? Is kinetic plus potential. Okay. And it is conserved. So I have delta k equal minus delta u. It will be u initial minus u final, okay? And delta k is what? Is k final minus k initial. Of course, k initial is 0 because they are at rest here. You see somewhere it says they are released from rest, okay? Is equal u final, u initial minus u final, okay? U initial minus u final. And I hope you know how to calculate u initial and u final from when you are given the configuration. Here we have only two particles, okay? So k final here is 2 times half mv squared, because this k final actually is of the system, which are the two particles. Each particle will have half mv squared. This mass is the same, and the speed is the same, and therefore this you multiply by 2 for each one of them, okay? Equal u initial, which is k q squared over r1 minus k q squared over what? Over r2, and this 2 with this 2 will cancel, and you divide by the mass, and v will be square root of what? 1 over the mass okay, k q squared over r1 minus k q squared over r2. Be careful, my son, here. R1 and R2 should be in meters, okay? So this should be in 0.01 meter, and the distance here will be So this is here, R1 will be 0.01, and this will be 0.02 because the distance doubled, okay? And the mass is given, it has to be in kilogram, 0.001 kilogram, okay? This is kg, and this is meter, and this is meter, and the rest, of course, microcoulomb, you have to change it into coulomb. If you do the calculation correctly, you find the speed of each particle to be 318 meter per second for each particle, okay? For each particle, 318 meter per second. Thank you.